We'll now be looking at the derivatives of trig functions. Here we have listed the three basic trig functions, sine, cosine, and tangent, that we have already seen derivatives of. Let's add to it with the remaining three trig functions. Now I want you to take a moment and look at these six functions and their derivatives and see if you can spot any patterns that might help you remember these in the future. So I want to point out that all of the functions that have negative derivatives originated from co-functions. When we started with cosine, our derivative is negative sine. When we started with cosecant, our derivative was negative cosecant times cotangent. And when our derivative was cotangent, we got negative cosecant squared. So that's one pattern you can keep in mind when trying to memorize these derivatives. Some other patterns you might have noticed: when you start with tangent, your derivative is secant squared. When you start with cotangent, you get negative cosecant squared. So very similar patterns between tangent to secant squared, cotangent to cosecant squared. We've also got some similar patterns with cosecant and secant. So the secant is secant tangent, cosecant is cosecant cotangent. So basically the same things there, just with the co-functions being different, as well as the negative sign getting thrown into the mix. But otherwise, very similar patterns in those derivatives, as well as with the original sine and cosine as well. If you keep those in mind, really, if you know those two, you could theoretically prove any of the others using the quotient rules or any of the other rules we've learned before. For example, we could write secant as 1 over cosine of x and use a quotient rule to move on from there and prove its derivative. Let's start with a basic example and evaluate the derivative of 2 secant of x plus sine of x. So we can use the constant multiple. The 2 stays in front. The derivative of secant of x is secant of x times tangent of x, plus the derivative of sine of x is cosine of x. And that's it. We're done. The mistake I often see that I want to point out for students to avoid is that I'll often see people write something like this. Do you see what's wrong here? The mistake is that the arguments inside these trig functions are missing. So this is totally improper to write. You always want to make sure you've got those arguments, you've got those variables that your trig function is referring to. All right, for our second example, we want to find f prime of t for f of t equals sine of t times cosine of t. This is a product. We are multiplying those two trig functions. So using the product rule to find f prime of t, I'll leave sine alone, multiply by the derivative of cosine, plus, this time I'll leave cosine alone, multiply by the derivative of sine. Evaluating those derivatives. Derivative of cosine is negative sine. Derivative of sine is cosine. So I have negative sine squared of t plus cosine squared of t. And that looks like where we should stop. However, this is actually a trig identity. Don't be fooled by the plus sign in the middle. This does not equal 1 because we have that negative in front of the sine function. Let me go ahead and rewrite this a little bit and see if that helps you recognize the trig identity we'll need to use. If I write the cosine first, cosine squared of t minus sine squared of t, perhaps you recognize that as a double angle identity. So this can actually be simplified to cosine of 2t using the double angle identity for the cosine function. So don't be surprised if when you're doing your homework and you go to check your answers, you see something very different than what you originally got Like here, it was tempting to stop at this step, but if you check your answer, they'd probably have this in the back of the book. So you might want to have some of your trig identities handy for you to check to see if there's any of those you can use to further simplify your answers. For example 3, we want to find f prime of x given that f of x equals x divided by secant of x. So this looks like a quotient rule. We have that division happening. So if we apply our quotient rule, we have secant of x multiplied by the derivative of x minus x times the derivative of secant all over secant squared. Evaluating those derivatives, derivative of x is just 1. Derivative of secant is secant of x times tangent of x, all divided by secant squared of x. So we've evaluated our derivatives, but there is quite a bit of simplifying we can do here. I see that both terms in my numerator have a secant in common, so I'm going to factor that out, which just leaves behind 1 minus x tangent of x. So we are able to cancel out one of our secants here, leaving us with 1 minus x tangent of x all over secant. Now, what if we had done this problem a slightly different way? So I'm going to do this again. Our original function was f of x equals x divided by secant of x. Some of you might have said, hey, I know that 1 over secant is cosine, so I could write this as x times cosine of x instead, and then I could have used the product rule to take this derivative. X times the derivative of cosine plus derivative of x times cosine, and had derivative of cosine is negative sine plus 1 times cosine, which just simplifies to negative x sine of x plus cosine of x. But these two answers look so different. How could they possibly be the same? Well, remember in your trig class way back when, where you had to verify that two different trig expressions were actually equal? We could do that here to make sure that these are actually the same answer and that they are both correct. So I'm going to go ahead and take the quotient and try simplifying this and hopefully get the same expression I got when I used the product rule. So if I take this 1 minus x tangent of x over secant, I'm going to choose to break that fraction apart. And a nice trick for simplifying trig expressions is to write everything in terms of sine and cosine. So 1 over secant, well, secant is 1 over cosine. Tangent is sine over cosine. And we have another secant. And simplifying those, I can take the reciprocal of this first term and just get cosine minus this would be x times sine of x over cosine of x. 1 over cosine, I can take that reciprocal. Look at those cosines canceling out. And we have cosine of x minus x sine of x. Let's compare. Those are now the same answers. So that shows that whether I had wanted to use the quotient rule or the product rule on this, I am getting the same answer in the end, even though initially the quotient rule looked much more complicated than my answer for the product rule. All right, our last example, we want to find the fourth derivative of x if f of x equals sine of x. So this notation here, this 4 in parentheses, the parentheses are what tell us that that's a fourth derivative rather than a fourth power. And we start using that for higher order derivatives because writing this as f 1, 2, 3, 4 primes of x gets a little messy. What if we needed to take a 20th derivative? We wouldn't want to write out 20 little dash marks there. So for higher order derivatives, we write them in parentheses as we did here. And to do that, we just start taking derivatives. So f prime of x is cosine of x. The second derivative of x is negative sine of x. The third derivative is negative. Derivative of sine is cosine of x. And then our fourth derivative negative comes down. Derivative of cosine is negative sine of x. So that just simplifies to sine of x, which, check it out, that's the function we started with. So the derivatives for sine and cosine, it turns out, are very cyclic. They repeat every fourth derivative, which is pretty cool.